So lesson 96, several different topics. Let's start off today by proving the law of sines. And to do that, we are going to use the area formulas that we have learned this year for finding the area of a triangle. We know that I could take 1/2 times one side times another side, and then the sine of whatever angle happened to be between those two sides. In this case, angle C is between sides A and B. Or I could have taken sides B and C, and then the angle between B and C would be A, so I'd have to use a 1/2 BC sine A. Or I could use sides A and C, and then it would be angle B that's in between there, so I'd have to have 1/2 AC sine B. Because it's the same triangle, I haven't changed that, the area better be the same no matter which formula I use. So all three of those things better be equal to each other. So to do my proof, I am first going to say that the top one has to be equal to the second one. So with the sine of C and the sine of A, and that's what I've written down here, that those two versions of the area formula have to be equal to each other. I know that I am trying to get to A over the sine of A has to be B over the sine of B, and that needs to be C over the sine of C. To get there, I am going to start with these two parts of the area formula being equal to each other. And by now, I think you guys know that I'd rather not work with fractions if I can avoid it. So I begin by multiplying both sides by 2. That means that I have AB sine of C equals BC times the sine of A. Max, what do you notice on both sides?
There's a B.
There's a B. So let's clean it up. Let's divide both sides by B, just so we can get rid of that. And now I have A sine C equals C sine A. And then I look back at my law of sines, and I want sine of the angles to be in the denominators. I don't want to have this sine C in the numerator, so I am simply going to divide both sides by sine of C so that I can get rid of that. And for that matter, I don't want sine A in the other numerator, so I'm going to also divide both sides by the sine of A. And then this one cancels, and I have A over the sine of A is C over the sine of C, and that sure looks like part of the law of sines. I have this first and last part are now equal to each other. I just need to get the part with B's in there. So I'm going to take another look at these three formulas. So far I have used the first two, but I need to use the one that has sine B in it. So I'm going to put that together with one of the other ones. I think I did it with sine C here. And set those two equal. And then I'm going to repeat the process. I am still not very crazy about fractions. So I'm going to multiply both sides by 2, which gives me AB sine of C equals AC times the sine of B. And Joe, what do I now have on both sides? I have an A on both sides. So let's divide by A and get rid of that much. So I have B sine C equals C sine B. And I don't want those sine of angles in the numerator, so I'm going to divide both sides by the sine of C so I can get rid of it on the left. And if I also divide both sides by the sine of B, I get rid of sine B on the right. And now I have another part of the law of sines. I have B over the sine of B equals C over the sine of C. notice that I have c sine c equals on both sides. So c sine c, c over sine c is equal to both of the others. That means all three have to be equal to each other by the transitive property. So we can say our law of sines is true. A over sine A equals B over sine B equals C over sine C. And that's what we want. Anybody with a question now? Okay, then let's maybe use law of sines, maybe use the area formulas that we've talked about, whatever it takes. And let's review how we're going to solve a problem like this. Some of you are doing great with these. Some of you get a little bit tripped up on how do you approach them. So this one gives two sides, the 18 and the 21, and it gives one of the angles, 65. They could ask us to find both of the other angles and the missing side, but they only ask us to find the two angles. And in addition, they ask us to find the area. So we need to get the missing angles. Our rule is we use law of sines if we can. If we have an angle and a side across from each other and we know the numbers for both. Is that true here? Can we use law of sines? So we know the 21 and the 65, they're across from each other. So we can say 21 over the sine of 65 degrees has to be 18 over the sine of angle A, and that's also the missing side over the sine of angle C, but we don't know either of those, so that's not really going to be helpful right now. So you guys are going to help me out with the calculator part here. We're going to do our cross product, 18 times the sine of 65 degrees has to be 21 times the sine of A, so if I divide both sides by 21, I have the sine of A, which means I need to take the inverse sine on both sides, must write down inverse sine of the messy big old fraction, 18 sine 65 degrees over 21 when you're writing this on your paper. That's what you enter on the calculator. That's what I need to see on your papers. So help me out here. What are we ending up with for this particular angle? Kim, did you get it already? Anybody else? 50.972. Give me a thumbs up, hands up, or something like that. I just always like to double check. I know how many times I hit the wrong key by accident and don't realize it, so if we double check, that's a good way to know that we're right. All right, so now we know angle A. How are we going to find angle C? Triangle sum. So store that real fast before you go on. And then we know that C will have to be 180 minus the 65 minus our stored angle A. And who has that? Elaine, you've got that? 64.028. Give me a thumbs up or down. Okay, looks like that's good. And I'm going to repeat my C just so it's easier to tell when checking which was which. So now we have both of the angles. Now we are supposed to find the area. So for a triangle, I have two choices of formulas. I have the 1/2 base times height that I've known for a long time. Do I know a base and a perpendicular height? No, so I better use the other one. Haley, what are you thinking? Is it still on radians from doing one of the trig problems, possibly? And are you in a document or Scratchpad? And is it saying degrees up in the top right corner? Okay, so you need to click menu and settings, or you may be able to just move your cursor to where it says radians in that top right corner and change that. Does it say degrees now? Okay, if you don't get it, I'll help you with it here in a minute. But we don't have any perpendicular heights that we know, so we probably don't want a half base times height. So we probably want that formula that we were using to do the proof of the law of sines. 1/2, do I know two sides? Yeah, I know the 18 and the 21. Do I know the angle in between the 18 and the 21? Okay, it is the C that I just found. So better hit store for this C. And punch that in and let me know what you get. We could just do 9 times 21 times the sine of C if you wanted to. Chloe, you have it already? 169.913. Seeing thumbs up, and this is area, so units are centimeters and square. So hopefully that was kind of a good review of putting some of those pieces together for those of you that have continued to struggle with that a little bit. All right, now let's move on to the binomial expansions. And I'm going to give you another formula, and it's going to look really weird when I first show it to you. But everything except for the numbers at the beginning of each term is exactly the same as what you've already been doing. If we are going to the nth power, we start off with the first term to the nth power. And then that exponent goes down by 1, and the other one starts going up, starts with 1, and starts going up by 1. So on the A's, I've got n minus 1, n minus 2. Those are going down. The B's, I don't have it all in the first one, and I have B to the first, B to the second, and so on. Emerson? No, just do this one next. It just happens to come from lesson 102 because we're jumping ahead to that, and I don't know what formula number this is now. That's just reference if you want to look something up in the book for more examples on how to do it. So the only thing that's different here is instead of going to Pascal's triangle to get the number that goes at the beginning of each term, you can now do it with combinations. Because as we reviewed the other day, those parentheses mean n choose 0, n choose 5. If I had n choose 7 with combinations, that would mean n factorial over, and I'd have two things in the denominator. I'd have 7 factorial, and I'd have n minus 7 factorial. So let's come up with our formula for the rth term, and we already know that for the rth term, we're going to, if we've got A and B, we're going to have r minus 1 over here. And we already know these need to add to what? N, right? Whatever our exponent is on this thing, we know that our exponents on the terms have to add up to that. That is not changing. So all we need to notice is that the first term is n choose 0. The second term is n choose 1. The third term is n choose 2. So if I want the rth term, I need to take 1 less than that term number as the bottom part of my combination notation, and as the exponent on the second term. So both of these are going to be 1 less than the term number. And do not mess with trying to memorize that messy exponent on the first thing. All this says is what I had right here, that the two exponents have to add up to the original exponent on the parentheses. So I want to do two examples. One that's very easy that you could do with Pascal's triangle, but we're going to do with combinations. And another one that throws one more new twist at you that I want you to start practicing. So if I have to the 14th, I could go to the 14th row of Pascal's triangle. I don't really want to. But that means I am going to have 14 choose something. And then I am going to have that times m to some power and k to some power. So Haley, if I want the 7th term, I do 14 choose what? And the 6 also goes where, Reagan? Where else do I put a 6? So I put a 6 in the bottom of the combination notation. Where else do I need a 6 on? On the k. Just like before, that last exponent is one less than the term number. Nate, what do my exponents need to add up to?
They would need to add up to 14.
They need to add up to 14, our original exponent. So everybody, what does m have to have for an exponent? So now all we need to do, and you guys are going to do this with your calculators for me, we have to write down that that notation means 14 factorial over 6 factorial, 8 factorial. And now you guys punch that part into your calculator so that I know what actual number to put in front of m to the 8th, k to the 6th. Jet, you have it already? Anybody else? 3003? So I've seen thumbs up there, so there is our answer on that one. Okay, one more that'll let us practice with this combination notation, but it's also going to throw the new piece at you. Up to now, in the parentheses, you have had one letter plus another letter. They can be extremely messy, first and second terms in that binomial. My first term now is not x, it is 3x. My second term is not y, it is negative 2y. And you keep the plus and minus signs with those. So now, my original exponent is 8. So I need 8 choose. Everybody, if it's the 6th term, what goes in the bottom of the combination symbol? 5, good. Then I'm going to have my entire first term to some power times my entire second term to some power. The 5 not only goes 8 choose 5, it is also the last exponent. Everybody, what does the first exponent need to be? Okay, so I need you guys now, we write down 8 factorial over 3 factorial and 5 factorial. Evaluate that for me. Helen, what'd you get? Anybody else, 56? Okay, but that's not our only number in there. We also have 3x times 3x times 3x, which means 3 cubed times x cubed. We also have negative 2 times y times negative 2 times y times negative 2y. So we have negative 2 to the 5th. And we have y to the 5th. So we have times 27 x cubed. You have to be careful when you have the pluses and minuses in there. This is negative 2 times negative 2, 5 times. So 5 negatives makes a negative 32 in there times y to the 5th. So now I need you guys to help me out. What is 56 times 27 times 32? I'll take care of it's going to be something negative. But you guys with your calculators, what do we get when we multiply those three things? Julianne, you have it already? Yeah. 48,384. Give me a thumbs up just as a double check. Others getting that? And then we keep our x cubed and our y to the fifth. Is that much making sense? Anybody with questions on that? All right, then the last part of this lesson is just going to be a couple of proofs. And so for this one, we're going to start out with copying down that nice left-hand side there. And somebody give me an idea of what we might do when you see that parentheses squared. What do you want to do when you see that, Cal? Okay, let's expand it out. So let's see, that would give us sine x times sine x would be sine squared of x. And then I'd have 2 of the sine x times cosine x. And then I would have plus cosine squared of x. Now I need another idea. Gavin, you see anything in that you might do? Okay, so sine squared and cosine squared is 1, so I have 1 plus 2 sine x cosine x. I know that I have a formula that says 2 sine x cosine x equals, or even cosine x sine x equals. So I'm not sure what I'm going to do. So I look at where am I trying to go. I need to get to 1 plus sine of 2x. I've got the 1. So somehow I want to get this other part to the sine of 2x. I'm a little confused what to do, so I'm going to do a little scratch work over here. I'll just kind of draw a line so I can do my scratch work. Do I have a formula for the sine of x plus x or the sine of 2x? What does that give me, Joe? If you have sine of x plus x, let's see, if we're not remembering sine of 2x, it could be sine of x plus x. Gavin? Say that again, just like if I do it. So if I did it as x plus x, I'd have sine of the first, cosine of the second, plus cosine of the first, sine of the second. So I get sine x cosine x plus cosine x sine x, which is just 2 sine x cosine x. Hey, that's what I want, right? So it is okay in a proof to go backwards. If I have 2 sine x cosine x, I can change that to a sine 2x, which is what I want. And you just haven't really had much where you've had to think backwards with some of your other identities, but keep that in mind as a trick. This one isn't really something new, but I'm just going to have you guys talk me through the steps. So we would begin by copying down that cosine to the fourth of x minus sine to the fourth of x. And help me out here. What are we going to end up coming up with? What can I start with? Kenny, you have any ideas of how we might start? Something I might do to that numerator? Yeah, because it's what kind of factoring pattern? Or how would I factor it? Or yeah, it's a difference of squares is what we call the factoring pattern. So I could say that is cosine squared x plus sine squared x times cosine squared x minus, oops, I got my x, minus sine squared x. And hey, that second one is another difference of squares. Maybe I'm going to end up wanting to repeat it and factor just that second parenthesis since it's got a minus sign in that. I don't know, maybe, but it's an idea. Before I decide, what can I do with the cosine of 2x? Don't we have a formula for that? Awesome. Okay, so do you want to do what I was saying and expand out that other parentheses? Reagan, you're shaking your head no. Why don't you want to do that? Yeah, let's just go ahead and cancel it now. I mean, I could expand that one out and expand that one out and then cancel all 4 of those parentheses, but that's a lot of extra writing that I don't need to do. They cancel now. So that means I've got just cosine squared of x plus sine squared x, and I need everybody shout out what's that equal, which is what we want. So everybody good there?